Now that we've covered the basic equation for molarity, which is the number of moles per liters of solution, there are two very important calculations that are going to use molarity for the rest of the semester. And the first calculation that we are going to use molarity in is the dilution. Dilution problems are when we are just adding water to a solution to make it more dilute or less concentrated. And the other very important calculation type that we're going to be doing using molarity is stoichiometry. And stoichiometry is when we are running a chemical reaction. So we're not just diluting something by adding water to it. With stoichiometry, we're actually running a chemical reaction. And so we're going to need to set up a stoichiometry dimensional analysis setup. And in the stoichiometry dimensional analysis, we will be using molarity as a conversion factor. So for a stoichiometry, I'm running a chemical reaction. And that means that I use a dimensional analysis. Setup. And in the dimensional analysis, molarity is used as a conversion factor. Okay, and that is in contrast to dilution. In dilution, I am not running a chemical reaction. I am just diluting a solution by adding water. So I'm not going to use a dimensional analysis setup for this. All I'm going to use is the algebraic equation. Molarity equals moles of solute over liters of solution. So it's important that we use the correct method to solve the problem that is required. Now with this in mind, let's talk about using dilution problems using molarity. So that's what we're talking about up here. If we have a solution and we are just adding water to it to dilute it, then we are doing nothing to the amount of dissolved solute in that solution. So it doesn't matter how much extra water you add to a solution to make it less concentrated. The number of moles of the dissolved solute are not going to change. It's not going to change how much of that salt that you have in there. It's just going to change the volume of the solution by adding water. So that's what this says here. Observe that the number of moles of dissolved solute would not change if we were to add water to the solution. However, by adding water, we would increase the volume. And because you're increasing the volume, you're increasing that denominator right there. And if the numerator stays the same and the denominator increases, then that makes this whole term get smaller. And so the molarity is smaller. It becomes less concentrated. And so therefore it decreases the concentration. So there is an equation that can help us calculate the new molarity or the new volume after you have done a dilution, taking advantage of the fact that the number of moles of solute does not change. So if the number of moles of solute is not changing, then the initial molarity, which we'll designate by M1, times the initial volume which equaled the number of moles of solute. The number of moles of solute does not change, so it also equals the final after dilution concentration, M2, times the final after dilution concentration, V2. And you can see that if M1V1 equals the moles of solute and M2V2 equals the number of moles of solute, we can simplify this into this equation, M1V1 equals M2V2. And this equation right here is called the dilution equation. And it's very important. We use it quite a bit. However, there is a challenge that students face because it is so useful and it's generally so easy to remember that students are often tempted to use this equation when they shouldn't. Students are tempted to use this equation not just for dilution, but they are also tempted to use it for stoichiometry problems as well. And this is especially problematic because sometimes the dilution equation will coincidentally give you the right answer for a stoichiometry problem. But very often it will not work. It will give you the wrong answer. And so, as a means to train you to use the correct techniques, we are going to ask you never to use the dilution equation for a stoichiometry problem. So that's what this is saying down here. An important warning. We only use this equation when we are just diluting, when we are just adding water and not running a chemical reaction. We do not use it when we are running a reaction and doing stoichiometry calculations, even though it sometimes accidentally works for stoichiometry. Using this equation for other stoichiometry problems is therefore considered bad practice, and usually will result in incomplete credit on assignments, even if it accidentally provides the correct answer. And again, the reason that we're doing this is we're training you to use the proper tools and technique for each task. So, let's do a dilution problem here. You have the general equation for dilution, M1V1, initial molarity times initial volume, equals final molarity after dilution times the final volume after dilution. So we've got a sample problem here. How many milliliters of a stock solution of 3.00 molar sodium hydroxide solution would be required to make 2.00 liters of a 0.100 molar solution? Now this is a dilution problem. How do we know that it's a dilution problem? First of all, we can tell that there is no chemical reaction being discussed. This sodium hydroxide is not being reacted with any other chemical. There's no chemical reaction being referenced. All we're doing is we're talking about making up a new solution with a new concentration from an original solution of an original concentration. So that's a clue that we are doing a dilution problem, and therefore we need to be using our dilution equation. One of the challenges of doing dilution problems is, first of all, recognizing that it's a dilution problem. And the second is that many students have difficulty recognizing which terms are associated with which of these variables in the equation. So I'm going to draw a little bit out here to help you get this set up, to help you think about this, and then I'm going to let you work on it. So it says how many milliliters of a stock solution of that would be required to make that. So it seems pretty obvious that this stock solution is what we're starting with. And indeed, a stock solution, the definition of that is It's a solution that is sitting in your stockroom or on your shelf already made up. Very often we make up stock solutions for storage at various concentrations because it's a lot easier to make up a new solution with a new concentration by working from a stock solution and just diluting it rather than having to get out the solid material, the solid solute, dissolving it, stirring it to dissolve, maybe overnight, and adjusting volume and all of that. It's often a lot easier just to dilute a stock solution that is already sitting on the shelf. So that's what we're going to start with. I'm going to draw a little bottle here to represent that we've got a stock solution sitting in the stock room, and that stock solution is 3.00 molar sodium hydroxide. And that's sitting on the shelf in my stock room. And then I'm going to try to make 2.00 liters of that solution at a different concentration. So over here, I'm going to draw a volumetric flask, and you've seen these. We've worked with these in the lab, I think. You remember what they look like. Volumetric flasks are highly precise pieces of glassware, and they allow us to make solutions of certain concentrations. And we want this volume to be 2.00 liters after we've made the solution. So the question is, how many milliliters of that stock solution am I going to take out and put in here so that it's down here in the bottom of my volumetric flask? And then I'm going to dilute it by adding water all the way up to this line. So the meniscus is sitting right on that line. So how much of this has to be right there? That's what I'm looking for. How many milliliters of that stock solution is going to go in there? Well, let's set up our dilution equation. M1V1 equals M2V2. And what we need to do is we need to rearrange that equation to solve for the unknown. So what is the unknown? Well, I know my final volume. My final volume has to be 2.00 liters. So I know that. I know my final solution's molarity. It's right there. So I know M2. I know my initial stock solution's concentration. It's right there. So I know M1. So it looks like they're asking me how many milliliters of that initial solution am I going to use. So they're asking me for V1. So I'm going to rearrange for V1, and then I need to solve for V1. I'm going to ask you to pause the video and go ahead and do that math, but beware, V2 is given in liters. And so when you solve for V1, you will get units of liters. But the question is asking for milliliters. So after you get your V1, you're going to have to convert that to milliliters. So go ahead and pause the video and do that if you would, please. Okay, coming back from pausing the video, we're going to go ahead and work through this problem. We're going to solve for the initial volume of the stock solution, and then once we get it in liters, we have to convert to milliliters. So let's go ahead and do that. I'm going to rearrange my dilution equation to solve for V1. That's just algebraically rearranging the equation. And now I'm going to start plugging in numbers. So the final or secondary molarity after dilution is right there, 0.100. The final V2 volume after I have diluted it is going to be the new solution volume, 2.00 liters. And my M1, my initial molarity, is going to be that molarity of the stock solution right there, 3.00 molar. And now I do the math, and I get 0.0666 repeating. And I need how many sig figs? Well, there's 3 sig figs there, 3 there, 3 there. So I'm going to round it to 3 sig figs. So that would be 0.0667. What are the units of this? Well, the molarity cancels out, and I'm left with liters, right? Am I finished with the problem? No, because it asks for milliliters. So I'm going to need to take that liters and convert it to milliliters. So let's do that really quick. 0.667 liters. 1 liter to 1,000 milliliters. And so I get 66.7 milliliters of my stock solution that I would have had to have used in the beginning. I would have dispensed it probably with a burette or maybe some other sort of, probably a burette would have been a good way to do this. A large burette. Dispensed the solution down here in the bottom of this 2-liter volumetric flask, and then diluted it up to 2.00 liters and mixed it really well to make sure that my solution was nice and homogeneous. By the way, this is an operation. This is something that is done in chemistry labs all the time. I remember working in a chemistry lab. I worked in one for 3 years, and we were doing this sort of dilution all the time. We became very, very familiar with this equation. Okay, that is how you would use the dilution equation to solve for an unknown. In this case, the unknown was the volume of an initial solution required to make a diluted solution of a particular volume. But you could rearrange this algebraically to solve for any of these. Just be very careful when you read the question. You want to make sure, number one, that it is a dilution problem, that you're not running a chemical reaction, you're just diluting something. And number two, you want to make sure that you are assigning the numbers, the values, to the correct variables in the equation.